Welcome everybody. Welcome at the session about milling cutter positioning. What is milling cutter positioning and why is it so important? Or is it still important? Because I remember when I was a young man, and I took my first steps in machining, this was a very important thing. This was a very important subject, but the question is a bit, is it still today? But today with all those fancy milling strategies and milling methods we have, is it still worthwhile talking about milling cutter positioning? Well, let me say like this. If I look around today in the machining world and I see all those 5-axis milling machines with all those sophisticated strategies which are being used, and if I listen to people and if I hear they still have issues with micro vibrations and too short, too live, and surface roughnesses that are not in line with expectations, then I wonder, could it be that perhaps this very old notion about milling cutter positioning is forgotten a little bit, and that could be, I'm just asking the question right now, that could be the reason we still have those minor things annoying us on the 5-axis milling machine. But milling cutter positioning, and again today, of course, I'm not alone here. I have the honor of addressing to you directly on the screen, but I have my friends and colleagues in the background making all these things possible from a technological perspective. Olivier, Viju, Alesia and Margarita, they are the ones making all of this possible behind the scenes. They are the production team, so I think it's important we recognize them for that also. And before I start talking about milling cutter positioning, perhaps a flashback to 2 sessions ago when we talked about milling strategies and where we had a paragraph or a chapter on cutting data. Just to bring it back in your head, a few things to remind when we talk about milling operations and the cutting data related to it. If we talk about how we select cutting data, there are 2 basic strategies that could be used here, or tactics I should say. We could work static unified approach to cutting conditions. That means that once and for all, we determine the cutting conditions for a milling cutter in a certain workpiece material for a certain application, and that's it. We have a feed and a speed and depth of cut, and it's fixed. That's static unified. Next to that, we have the dynamic modified cutting data approach. People refer to this approach very often in a shorter way. They call it dynamic milling. That's an approach where I would say moment by moment we look into the actual situation a milling cutter is in, and related to that we look at our cutting conditions and we modify them if needed, if wanted, if desired. If we do that approach, and today it's possible to do that approach, because in the past when we were talking about conventional milling machines, of course this was an impossibility. We knew about it, but we could not really apply it. Today, with all the modern possibilities we have on CNC machines and digital steering of stuff, this is in reach as an approach. That's the second method. And I'm going to come back later in this presentation on which one we should prefer. Another point I draw your attention on is that we have to be very careful that we apply cutting conditions, cutting data, the way they are defined. And there are 2 ones which have very big impact here. One is depth of cut, radial depth of cut, the width over which a milling cutter is in contact with workpiece material, measured parallel to the radius line of the milling cutter. And I give you here an example. Imagine a milling cutter that is doing this dotted shape, and the milling cutter comes from below and is milling upwards, while in the beginning you have a radial depth of a certain value, and the moment the milling cutter enters a corner, suddenly you are confronted with a radial depth of cut which is in line with how it is defined different. Now, when one of the cutting conditions for a milling cutter is changing, in this case in process, while the cutter is cutting, that has consequences, and we have to be aware of that. We have to be aware of if we cannot compensate for this, and that was a principle we talked about in the previous session. If you couldn't participate in it, perhaps you should watch the recording of it. But that's a situation where in process we notice one of the cutting conditions changes, and to make sure the milling cutter is still cutting in balance, we have to compensate by changing something else, by changing another cutting condition. That is the basic principle of dynamic milling. It's based on compensation techniques. It's also, when we look to the type of milling, if we do linear milling or non-linear milling as an operation, linear milling means that the milling cutter, the center of the milling cutter is following a straight line over or in a workpiece. We refer to that as linear milling. If we do non-linear milling, and you see here two examples which are the easiest non-linear milling situations. It's circular milling. The milling cutter is following a circular line, internal or out external, in a workpiece or around the workpiece. Well, also in this case, the definition of the radial depth of cut is not the material oversize, which people very often by mistake think it's the radial depth of cut in this case. No, it's not. Radial depth of cut is the width over which a milling cutter is in contact with workpiece material, measured parallel to the radius line. That means internal nonlinear milling, radial depths of cut will be bigger than the material oversize. External nonlinear milling operations, the radial depth of cut will be smaller than the material oversize. It's something to be aware of. And here I have to share a bit of a disappointment I have, because 2 sessions ago I asked the people listening to the presentation about the feet. Where should we apply feet? What is the definition of feet? And you see here 2 situations, and I move a little bit aside, you can appreciate the picture fully. You see here 2 examples of a circular milling operation. And in the situation to the left, I put the feet in the center of the milling cutter, at the center line. And the situation to the right, I put the feet at the periphery of the milling cutter. And I asked then the question, what is correct? Where do we put the feet in nonlinear milling? Do we put it at the periphery of the milling cutter, or do we put it in the center line of the milling cutter? And the majority of you, or at least the people who participated in that session, they said we put the feet at the periphery. Now, sorry to say, but that's wrong. That's wrong. Feet is defined, and let's go back to linear milling, the easiest way. Feet is defined as the movement we have to give to the center line, and I emphasize center line of a milling cutter, so that every tooth of a milling cutter cuts correctly, in a balanced manner. And if a milling cutter is following a linear line or a non-linear line, that does not modify the definition of feet. Feet is movement of a center line. That means the non-linear examples here, the one to the right and the one in the middle, it's the one in the middle where feet is applied correctly. And for your information, if you use cutting data software like Suggest from Seco, be aware of that when we talk about feet, we apply the definition correct. In case of nonlinear milling, circular milling, the feet is the movement of the center line of the cutter, not the movement of the periphery. But that perhaps is a subject on its own. I should not spend too much time, because today the real subject is milling cutter positioning. But when we do milling cutter positioning, please be aware of the definition of cutting conditions, cutting data, and apply them correct. Milling cutter positioning, What do we talk about? Well, basically, there are three ways we can position a milling cutter compared to a workpiece. You have here in the picture, and I move aside again that you can fully appreciate the picture, you have situation A, situation B, and situation C. A is referred to as side milling or contour milling, up milling. The one in the center is called central milling. And the one in the bottom is called contour milling or side milling, but then down milling. And these are basically a little bit theoretical, but anyway, these are the three basic choices we can make when we talk about milling cutter positioning. And perhaps, again, let's try to have a bit of a dialogue here. If you think on your experience, what do you think? When we look at the performance of the milling cutter, first question, if you look at the performance of the milling cutter in general, does it cut without vibrations? Is the surface roughness okay? All that type of things. What do you prefer, A, B, or C? Please share it in the comments to this, that we can see how the opinions are you have on this. So you can put there just one, A, B, or C. For best performance, do you prefer side milling, up milling, central milling, or side milling, down milling? Another way of looking is from a more economical perspective, the cost thing. Which position do you think offers you lowest production cost? Again, A, B, or C? It could be, that's an option D then, that you say, I don't see any difference. Does it matter? Already jumping conclusions a little bit perhaps here, I can tell you it does matter. It absolutely does matter. But let me know your opinion. 2, A, B, or C. Which one is most productive? Which positioning is fastest milling? And I have to admit, I'm asking here questions which are perhaps, it's a little bit early to ask the question, because the next session in getting technical is about ship thicknesses, and to really appreciate the questions I'm asking here, you also have to draw in the things we are going to discuss when we talk about ship thicknesses in milling. But anyway, I ask the question here, what do you think? What's your feeling? What's your experience? Doesn't it matter, or does it? And which one is fastest then? Which one is most productive? And last one, the thing we always talk about, machining people, we love talking about tool life of cutting edges. Which of these positions do you think gives us best tool life of the cutting edges? Which of these positions will lead to the least wear on the cutting edges after a certain time unit? With other words, longest tool life. Really, I'm really looking forward to see your opinions a little bit later on in the comments about these questions. But this is what we are going to talk about during this session. How do we position a workpiece and a milling cutter compared to each other? Three basic choices. If I approach it a bit theoretical, side milling, central milling, and in side milling you have side milling, up milling, side milling, down milling. Down milling is, and you have to try to imagine it, when you imagine that a milling cutter is cutting a chip from thick to thin, we call it down milling. Down milling and C milling, some people refer to it also. In the opposite case, when a chip is formed from thin to thick, we call it up milling, or some people refer to it as conventional milling. There are all kinds of words to distinguish the two. First, a few words on up milling, down milling. If I look to the two situations, up milling, a chip is formed, try to picture it. A chip is formed from thin to thick. That is a situation where we talk about up milling, while in the opposite case, what you see in the bottom here, when the workpiece is positioned in the bottom, here you see, or you can imagine that a chip is formed from thick to thin. That we refer to as down milling. Well, in general, from a milling cutter perspective, from a process perspective, I mean that the machining operation functions in the best possible way. Down milling has preference. Down milling offers basically only advantages. It will give us a longer tool life. The ships which are formed land behind the milling cutter, defined as the way the cutter is moving over a workpiece, which gives us less danger for recutting of ships, especially important when that risk is there. It's less critical for workpiece fixturing. Ships are being removed easier. So only advantages. Upmilling today is limited, I would say, to situations where you are unfortunately perhaps confronted with somewhat older machines, machines where there is still, or where there is backlash on the table spindles. There you have to be careful with down milling, so less stable machines, somewhat older machines, less maintained machines. Some weaker workpieces, some specific workpiece materials where we have to try to find a compromise between certain things. Specific cutting materials, somewhat harder cutting materials, it could be an issue if we do down milling, but I would say in general the situation 2023, instinctively you should think on down milling approaches. Up milling is very, very specific. The thing with up milling is that, and I try to show it here with a milling cutter. You see to the right where you see slow motion how a milling cutter is working, and you have to focus on where cutting edge starts cutting. Theoretically, even practical, in upmilling you have a situation where we try to make that a cutting edge cuts material with a thickness of 0. And that doesn't work. Now, a milling cutter, a milling machine is strong enough, there's power enough behind it to make the cutting edge cuts. But that goes at the expense of things. So upmilling, it's all about starting the operation, pushing a cutting edge into a situation it cuts with a thickness of 0. And that normally doesn't work. And especially today when we talk about cutting edge geometries, which we play with that, which is a subject of one of the upcoming sessions we have, where we are going to talk about cutting edge geometries and how we should work with them. Workpiece materials, conditions of workpiece materials play an important role here. Think, for instance, if you have to machine superalloys, strain hardening materials, where you push a cutting edge each time again through a strain hardened layer which has been formed. In general, try to avoid this. Try to avoid it. The opposite situation, that a cutting edge cuts from a certain thickness to thickness 0, is less unfavorable for a cutting edge. So that is what we have to bear in mind now. Now, central milling, I always say central milling is a bit for people who cannot make up their minds. Should I go up milling or should I go down milling? Then people say, okay, put the workpiece nicely in center of the milling cutter. Let's do it like that. You know, when I was a young man, we were even taught sometimes to measure if a workpiece is really in the center of a milling cutter. Now, honestly, this central milling, where you have a part up milling and a part down milling, and true central milling is that it's symmetrical, that the up milling part and the down milling part of a milling cutter is of the same dimension, is very unfavorable. And let me try to illustrate you that by saying, imagine you have to the left central milling and to the right you have or up milling or down milling, whatever one you use. Well, in case of central milling, you have a situation where a milling cutter part of the time is pushing the workpiece ahead of it, and part of the time it's pulling the workpiece towards the milling cutter. And that can create a situation where milling cutter and workpiece starts to do this. And as I show it here, it's a bit overdone. But this situation where you start to have a relative movement of milling cutter and workpiece compared to each other, while the milling cutter is moving forward, that potentially leads to micro vibrations. And micro vibrations, we have been talking at one of the previous sessions already to that. Trust me, you don't want micro vibrations. Chipped cutting edges, short tool life, bad surface roughness, the risk that you enter in a shatter situation, only negative things can come from micro vibrations. So the situation to the left is to be avoided. To the right, you have a situation where mostly the milling cutter is pushing the workpiece ahead, which is the case in up milling. In down milling, most of the time, mostly the milling cutter is pulling the workpiece towards the milling cutter, but you don't have the situation of the relative movement. And that's the only thing you have to remember. You know, there is a very typical situation where you always have central milling. You can't avoid having central milling, and that is when you use an end mill to do slot milling. And I think most of you know all the issues you can have with slot milling. That milling cutters are vibrating, breaking, cutting edges break off, and so on. It all is very basically coming back to what you see here on the screen. The potential relative movement of milling cutter and workpiece. Another thing to talk about or to try to imagine is what we call simultaneously cutting edges, simultaneously cutting teeth, milling cutter teeth that cut at the same time. To talk about this, we first have to define two things. A milling cutter has a pitch angle. A pitch angle, that's the angle between two teeth. Simple. Some milling cutters have differential pitch, which means that the pitch angle is not a constant value for a milling cutter, but some teeth are closer than other teeth. We do that to avoid vibrations. So you have the pitch angle and you have the arc of tool engagement. The arc of tool engagement is the angle over which a milling cutter is in contact with workpiece material. Now, why do I want to have a lot of teeth at the same time cutting? But that is to make variation in cutting forces lesser. If you have more teeth cutting at the same time, the total force will be higher, but the variation, because cutting forces in milling are never having a constant value, they go up and down. Well, that variation between minimum and maximum gets smaller and smaller and smaller when you have more and more teeth cutting at the same time. If you can manage it to have more teeth cutting at the same time, you have less vibration risk, you have better tool life, better surface roughness, less risk to enter a shatter situation, and so on. Now, how do we make that more teeth are cutting at the same time? Well, basically, we have to look here at the radial depth of cut, and we have to look at the diameter of a milling cutter. In practice, very often we combine the two, and we talk about the AEDC ratio. For instance, if you have a milling cutter diameter 100 and you have a workpiece width of 30, we say that we have an AEDC ratio of 30%. 30 divided by 100. 30% of the milling cutter is in cut. Well, if you have an AEDC of 100%, with other words, for a given milling cutter, you make that the radial depth of cut is big, you have more teeth in cut. If for a given diameter of a milling cutter you reduce the radial depth of cut, you have lesser and lesser teeth simultaneously in contact, cutting. So, trying to have as many teeth as possible cutting at the same time means you should, if the milling cutter is a given element, you should try to go for big radial depths of cut. Now, if you say, yeah, wait a second, my radial depth of cut is fixed, I cannot play with that, then you can play with the DC, the diameter of a milling cutter, the other element in the AEDC ratio. And what we see then is, if you reduce the diameter of a milling cutter, you will have more teeth in contact at the same time. In both cases, we play with AEDC ratios. In general, having a lot of teeth cutting at the same time means that the AEDC ratio should be as close as possible to 100%. If you go away from that, be aware that you can end up with some issues with vibrations and so on. Now, next to the diameter of a milling cutter as a variable or a potential variable, and the radial depth of cut as a potential variable, there is also how you position the workpiece compared to the milling cutter. If you put a workpiece centrally before a milling cutter, you have a certain arc of engagement. But if you put a workpiece more and more sidewards, up or down milling doesn't really matter here. What you see is that kind of free of charge, you receive that the arc of engagement increases. So by moving a workpiece sidewards, you create a situation that more teeth will cut at the same time, simultaneously, which means that the milling cutter cuts more in balance. Now, quickly in between, there's also something we refer to as cutting-edge positioning. What is cutting-edge positioning? Cutting-edge positioning is very simple. Some people refer to this as the cutting geometry of a milling cutter. It's how we position compared to the center line of a milling cutter, the reference line of a milling cutter. It's about how we position the actual cutting edge. And if we talk about cutting-edge geometries, basically we have three families. We have double negative milling cutters, we have positive negative milling cutters, and we have double positive milling cutters. It depends on how a cutting edge is positioned compared to the axis of a milling cutter, the central line, and compared to the radius line. This is just some information you need to know each time you use a milling cutter. I think it's something you should know about the milling cutter you use. What is the basic family in which the milling cutter is classified? Is it a double negative one? Is it a double positive one? Or is it a positive negative geometry? Because to fully appreciate the next chapter, here you have to be aware of which type of cutting edge positioning you have. Because if we look to a cutting edge can have four phases. It's not cutting, it starts cutting, it is cutting, and it stops cutting. Now, when a cutting edge is not cutting, that's easy. When a cutting edge is cutting, okay, things are more or less in balance. What is dangerous for cutting edges is the start and the end of the operation. When a cutting edge enters the cutting phase and when a cutting edge leaves the cutting phase. In case of milling, we have, for each rotation of a milling cutter, every cutting edge goes through those four phases. A cutting edge, when it's at the back, it's not cutting, then it suddenly starts cutting, it is cutting, and it stops cutting. The situation where a cutting edge starts cutting we refer to as the entry phase, and where a cutting edge stops cutting we call the exit phase of a milling cutter. Now, let me start with the situation entry. Here again you have my three possibilities. Side milling, up milling, central milling, side milling, down milling. The red line each time is the phase where a cutting edge enters the workpiece, where you have kind of an impact, and related to the positioning of a workpiece, also related to the cutting edge positioning, you can have favorable or less favorable situations. I would say in general the worst situation is central milling, where the risk that you have full impact I hope the picture illustrates better than I can explain it. You have full impact of the rake phase on a workpiece is not so favorable. Side milling, up milling or side milling, down milling, the situation is less risky. But in general, entry phases nowadays is not so critical anymore, I would say. as long as you follow instructions for correct cutting conditions, normally present carbide grades can handle impact situations. Exit is something else, where cutting edges leave a workpiece, what is referred to as exit. See the two red lines that indicates where on a workpiece the cutting edge leaves. Exit is a different story. Before we continue here, very quickly, we talk in this context about exit angles. What is an exit angle? An exit angle is the angle compared to the central radius line of a milling cutter, where a cutting edge leaves the workpiece. The situation upside, up milling, side milling, when the workpiece is on top here in the picture, we talk about an exit angle indicated on the picture, and the exit angle, by definition, we claim it's a negative exit angle. The opposite case, when a workpiece is positioned downwards, what you see in the bottom of the picture, the red line, also there we have an exit angle. In this case, it's defined, that's the convention we use in this, it's referred to as a positive exit angle. Now, what's going on at exit is that try to imagine, here you have to try to imagine the physical process of machining. A cutting edge is cutting, there is pressure, and most of the cutting materials of today, they have higher resistance against pressure loads on acting on it, so that's okay. But when a cutting edge leaves the workpiece, you kind of, for a fraction of a second, but each rotation again, for a fraction of a second, it's could happen that like pressure changes into tension, that it's like there is pulled on a cutting edge, and most cutting materials of today, they have no resistance whatsoever. So what could happen at exit is that kind of your cutting edges, and now I am exaggerate, I know, but they kind of explode when they leave a workpiece. It's like they are pulled apart when they leave a workpiece. And that is something to worry about, because if we look to the reality, what you see here, and I try to visualize it, the vertical line here represents tool life. The horizontal life represents exit angles. To the left, negative exit angles. To the right, positive exit angles. And let me start with the situation up milling. And when you see then, the red line represents tool life. And then you see if you have big exit angles, negative exit angles, the workpiece is towards the external part of a milling cutter, the periphery of a milling cutter, you have a certain tool life, but as the exit angle approaches zero, when in this case one could say the workpiece moves to the center of a milling cutter, what you see is that your tool life goes down, goes a bit dramatically down. And if you move the workpiece further from, in this representation, upwards towards downwards, from up milling to down milling, what you see is that after a while, tool life goes up again. So it seems there is somewhere a zone of exit angles where your tool life is very negative, affected. Remember, this type of test, one could say, is done with the same cutting conditions, the same milling cutter, same cutting conditions. The only thing I do is I move the workpiece compared to the milling cutter. I change the milling cutter positioning. And you know what is happening is if your exit angle approaches zero, and when a cutting edge comes close to that zero exit, the ship is at its thickest, one could say. That means the pressure is highest, so the load is high, and if then suddenly that load falls away, because the cutting edge comes out of the workpiece, it's a heavier explosion. Your tool life is limited by shipping. In some cases, even by breakage of cutting edges. So the advice here is rather simple. Stay away from this zone. If you value long tool life, If you don't want that your tool life is negatively affected by premature shipping, premature breaking of cutting edges, kind of you can do whatever you want, but make sure the exit phase, the phase where cutting edges come out of a workpiece, are not in a zone. And this is a bit of the beauty of this, because this zone can be rather easily defined as a zone having roughly half of the diameter of a milling cutter as width, and it's centrally positioned compared to the milling cutter. This, in red marked zone, the exit phase, the side of a workpiece where the cutting edges come out, should not be in. It should be above it, but that's not so nice, as that is very firmly up milling, and we don't like up milling. See, one of the things I already said. Down milling is much more preferable, so the workpiece should be downwards in this picture here. Based on all this type of things, and it's a subject we partly talked about last time also, but all the things people say, all the advice people give you about how to start an operation, how to end an operation. Should you use radial entry? Should you use tangential entry? Or the opposite, radial exit? It all has to do with these things we talked about milling cutter positioning. I'm pretty sure some of you have seen somewhere on internet or a picture about those so-called entry situations: straight entry, curved entry, tangential entry, radial entry. Now, it has all to do with the principles we talked about here. It's all about how do I position a workpiece, how do I position a milling cutter so that cutting edges, so that the milling cutter can work in best possible situations, not only when it's doing the actual application, but also starting the application and ending the application. And while I'm talking, I give you all kinds of examples. I'm pretty sure you have seen it somewhere in a technical guide, and perhaps some of you asked yourself, why is this? What are we talking about here? Is it really so important? Yes, it is. It has to do with the things we talked about. And in some cases it's less important. In other cases, I think mainly when you have milling operations in stainless steel, superalloys. If you have milling operations in forged workpieces where they are very difficult to machine skins, the state of the machine you use, all of these are the critical factors here that decide should you spend a lot of attention to this or not so much attention. These are things where we talk about acceleration, deceleration of machines. Last time we also spent some time on this. Know exactly what is your machine doing when you start an operation, when you end an operation. What is your machine doing when a milling cutter is coming in a corner? Evaluating all this and taking the correct measurements to avoid problems coming from the behavior, for example, of a machine tool. All of that goes back to milling cutter positioning, insight in what is happening there. So if we look to milling cutter positioning, what you see here is a bit of a theoretical, I took it from a technical guide about face milling, where we say, okay, if you have a face milling cutter, if you have a workpiece, well, the ideal world is represented here in the picture. And I know it's a bit theoretical. But okay, next to theory come the expertise you all have. But in theory, we say the milling cutter should be 25% bigger than the radial depth of cut. The workpiece should not be positioned centrally in front of a milling cutter. There should be some overhang on entry. There should be some overhang at exit. The overhang should not be symmetric. There should be less overhang on exit, and there should be more overhang on entry, and so on and so forth. What is behind this are 5 things, I would say. If possible, and in 95% of the cases it is possible, apply down milling. Only advantages. There are some specific cases where we do different. Avoid for sure symmetric central milling. you only have problems with that. Or problems is perhaps a big word. You have issues with that. That's why slot milling with an end mill is a bit of a complex operation. Because there you have symmetric central milling. Maximize the number of teeth simultaneously cutting by using big radial depths of cut compared to the diameter of a milling cutter, or by using smaller diameters of a milling cutter compared to the radial depth of cut. The AEDC ratio is what I'm talking about. And perhaps if you say, yeah, I can't work with either of them, they are fixed, yeah, then try at least to put a workpiece not central but sidewards compared to the milling cutter, because then you widen the arc of engagement and you simulate, not simulate, you create a situation that more teeth are cutting at the same time. Consider wisely exit situations. Think on the danger of exit angles in a case roughly half the diameter of a milling cutter wide, centrally in front of a milling cutter, where you should try to avoid that cutting edges leave the workpiece. And in all these cases, if you can do it, if you don't, if it's not possible, okay, live with it. But use, where possible, dynamic milling concepts. With other words, if you see one of the cutting data is not in line with what I was hoping for, and one of the cutting data could be the milling cutter positioning also, it's a cutting condition. Yeah, compensate by changing something else. Use dynamic milling concept thinking is my fifth and perhaps most important statement here. Now, of course, there are challenges for you. There's that so-called interrupted cutting. Interrupted cutting is a situation I try to simulate here. You have a milling cutter. Think on motor blocks of combustion engines, where very often they do a face milling over the motor block, over the cylinder holes, and then you have kind of this situation where a milling cutter can be simultaneously in 2 or 3 different situations. Here you see part of the time a milling cutter is cutting up milling, side milling, up milling, part of the time is cutting central milling, and part of the time it's cutting down milling, side milling. Yeah, on what situation now should you focus on? This is a challenge. And this is where expertise looks around the corner and should help us. Because here you have a situation, and I try to let you feel a bit what you are facing here. And I don't know if there are people here with some experience in a typical example I gave, face milling of the head of a motor block over the cylinder holes, where a cutter starts what people call then, the cutter is jumping, is doing this. And that has to do with that a milling cutter is confronted with 3 different situations at the same time, which leads to different types of loads acting on cutting edges. And as I said, here it's about expertise and things. But I think we should stop here and see what you had to say in the comments. What did we talk about? We talk about something which is, when I was a young man, very important. Then it faded away a bit. But I think still today, with all the fancy stuff we do in milling, that it's still worthwhile thinking on it. When you evaluate a milling application, especially when the result of it is not to your likings. Vibrations, surface roughness, shipping of cutting edge, and you think, I thought on everything. I have the most modern milling cutter in the world. I have the most sophisticated cam system in the world, and still, well, next time you have a look at a milling cutter operation, put your milling cutter positioning glasses on and up milling, down milling. What exactly are you doing? Aren't you by coincidence doing central milling? Did you select your milling cutter? Did you select your radial depth of cut in such a way that you maximize the number of teeth cutting at the same time, simultaneous cutting teeth? Did you think on exit failure? That the cutting edge, and I know my word is too heavy, but anyway, that the cutting edge is exploding the moment it leaves a workpiece. And as I said, as perhaps it doesn't sound so important here, but imagine every cutting edge, every rotation again has to go through the situation of exit. And that if the exit is unfavorable, yeah, you will see on a macro scale the consequences. Short tool life, shipping, breakage, and so on. And the fifth one, think dynamic milling. Whatever you select, think on if one of the things is not what it should be, compensate by modifying something else. Try to bring balance again to the situation. Fully appreciating that we are going to, hopefully I meet you again the next session when we talk about ship thicknesses. Because then we can fully appreciate the things I have been talking about here. But first, let's see, what questions came in about this subject. I have here a question from Sagar. And the question is how to give depth of cut. To be honest, I don't understand what the question is. How to give depth of cut? What parameter we can use? Sahar, can you put in comments some extra information? Because sorry, I do not understand the question here. The second question, how can we do upmilling on a conventional machine? Now, that the machine is conventional is not the thing here. The real thing is, can you move the table spindle without backlash? And on the more modern conventional machines, there is an how to say, that's not equipment, but there is a possibility to take, and I translate now in English, but to take up the backlash and put it in front, and then you can do upmilling on a conventional machine without any problem. So it's not about that the machine is conventional or not, it's about the question, can you move the machine tables without backlash? That is really the critical thing. Another question is, for which specific materials is upmilling suggested? Think like that. If you have a situation where the cutting edge starting the operation has to go through a skin, which is harder, which is more abrasive than the normal material. Let me give you some examples. A forged workpiece where you have the forging skin. Cast irons where you have the casting skin. And if you have a situation that the cutting edge has to go through the skin starting the operation, then often I should not say, but in some cases, down milling will lead to shorter tool life due to impact breaking or shipping, and then up milling could be the least of two harmful situations. Fourth situation, at exit we see more vibration at hard part milling on conventional. Yes, possibly. But here also to form a real opinion on this, I need to know some more information. Do you talk about micro vibrations, with other words, vibrations coming from the process, or do you talk about the classic shatter vibrations coming from the machine. Because depending on what we talk about, I can agree with this statement or I have to disagree with this statement. And then if we operate with lower feed rate in dynamic milling, does it that's an interesting one. But I'm going to be nasty. I'm going to answer that question with the next session here. Because to answer this, I have to make sure that you first know what we talk about when we talk about ship thickness, average ship thickness, equivalent ship thickness, that type of things. But let me answer a little bit in general. If your feeds are too big, that's going to limit tool life. And that's due to mechanical phenomena. Overloading, cutting edges, mechanical. If your feed is too little, you're also going to suffer from short tool life. But then it's not mechanical overload, then it's thermal overload, kind of. So, yes, but I should explain more, see next session. But I think this is a truly very good question. How does affect milling cutter positioning the FFT diagram? Sorry, I don't know what an FFT diagram is. Can you please let me know? Which are most suitable insert milling cutters for FRP materials? Yeah, that is a question much too specific to give you a very generic answer here. If you allow me, we can continue this after this session, because then I need to have more information on what exactly are you talking about. Then yet another question, does negative rake inserts require higher feed compared to positive inserts? No. Why? I suppose you talk about the macrogeometry, not the microgeometry, because then sorry, this question also deserves that you are a little bit more specific if you talk about negative cutting edge geometries or negative truly rake geometries. In one case, yes. In the other case, no. Then another question. It becomes difficult to identify up or down milling in solid dynamic milling. Yes. I fully agree with that statement from Durgamadab. That is exactly what I said in the beginning of this session. You know, basically I said people are so much focused on the sophisticated stuff, 5-axis milling and that type of thing. And trust me, before we end this session, I'm going to give an illustration of the statement here made by Durgamadab. I hope I pronounced the name right, because that is exactly what this is all about. We stand there, we look at it, and it's sometimes so difficult to recognize what are we looking at now. Do we see up milling or down milling or central milling, or what is it now? A statement, if we increase the RPM and decrease the feed, does it help in central milling? From a technical perspective, it could help, of course. In general, it will help. On the other hand, you have to ask yourself the question from an economical perspective, from a productivity perspective. If you reduce the feed, that means you go slower, but you are clever. At the same time, you increase the RPM, so you compensate for loss in production. But if you increase the RPM, your cutting speed goes up, and that makes that your tool costs go up. I don't say necessarily wise your machining cost, but your tool costs go up. So, yes, it helps, but it comes with a price, is my answer to that. Then a question from Daniel. I do get some difficult materials from time to face mill. I will keep your advice in mind, especially the... okay. thank you very much for the appreciation, I would say. Because, face milling is perhaps the milling cutter where this displays most, because as I said, an end mill, if you use it as a side mill to do contour milling, you automatically avoid central milling. And if you have an end mill in slot milling, you always have central milling. There you can't avoid it. It's But a face mill, you can play with diameters, you can play with positioning, and I like the statement difficult materials here, because of course the more difficult the material is, the more you will see the differences between best method and lesser good method. Perhaps Daniel, share your experience when you tried it, if it worked for you, and let us know. Is there a next question? I have to keep my eyes on the time also. A question from Vizal: is there any strategy for cutter positioning for different approach angles? Yes. No. You have the different strategies, but let me put like this. The difference between the worst and the best, when you have smaller approach angles, is less critical than when you have bigger approach. When you have a 90-degree milling cutter, strategy is crucial. If you have a high feet milling cutter where your approach angles are rather small, it is important but less critical. Then there is a statement from Laurent. What conditions shall we have to take for a part with many holes? That's a difficult. This is in general. I'm going to give you a very general answer. You have two ways you can go here. You can go for a very small milling cutter and maneuver through the holes, around the holes, use the numerical approach. That's one possibility. The other possibility is go for a big milling cutter, a strong one, and move over in one big go. Which one will lead to best result? Again, I can't say here, but I would say think smaller diameters and think numerical control machining, where you can program the milling part, the tool part, as such that each time again you have best possible approach. If that is not possible, use a big milling cutter, a strong milling cutter, and then don't worry too much and just move over. Of course, the last one has potentially the risk that there will be very heavy burr formation, or that you have workpiece edge breakout with the more ductile materials, or the less ductile materials, sorry. So there are pros and cons here for I don't think we will be able to handle all the questions here, because they start to come in. Question, what do you mean under micro vibrations? The traditional vibrations you refer to also that could lead to shatter and so on are vibrations due to that the whole milling cutter compared to the workpiece is making is bending, and due to the bending it starts to swing, kind of. And that can lead to a macro vibration, as it is referred to. In the end, it could lead to chatter. A micro vibration is a vibration that comes from that. It's not really. It's not having to do nothing with bending. It's just that a cutting edge and a workpiece, instead of moving like this, they move like this. Due to entry, due to exit, that type of things. And that movement could lead to that it starts to be rhythmic, harmonic. And then we talk about a micro vibration. Micro vibration, I always say it's dangerous things. You don't see it, you don't hear it, but it could be very deadly for cutting edges. I hope, comparison makes it clear. And then seeing the time, okay, a last question. For the questions I did not answer, or for the questions I say I need more information to take care of, let's agree after this session in the comments we continue to talk about, and I try to formulate answers as good as possible for every question here. But okay, a last question here. Downmilling in conventional machines sometimes becomes a challenge because downmilling draws more. No. Sorry to be so categoric, but the statement here from Duramadab, no, I do not agree with that. You have impact situations in downmilling, but the power as such is not noticeable affected by that. But this statement deserves more as me saying no. This deserves that I explain more in detail. And what I propose here also is that we continue this discussion after this session, because even if I'm so categoric saying no, on the other hand, this is a very interesting subject to exchange thoughts on. So I hope I meet you afterwards in the comments and we continue this discussion here. My time is up. I already passed it even, sorry for that, but yeah, as you could notice, I'm very excited about this subject, because I do think it's one of these cutting conditions. It's a bit old-fashioned, but it's one of these cutting conditions that helps us a lot in understanding how a milling cutter behaves during an operation. And if the milling cutter behaves inappropriate, leading to short tool life, vibrations, micro vibrations, shipping, it's worthwhile spending a few seconds on what is the milling cutter exactly doing right now. And it can be a challenge, as one of you said, because I let you enjoy 2 examples of 5-axis machining. And the question is very simple, to the left and to the right. What do we see? Do we see up milling or down milling or central milling? Is it continuous, or do we see sometimes one and sometimes the other? What exactly do we see here from a milling cutter perspective, a milling cutter positioning perspective? And it can be difficult. I hope to see you next time, because next time we have a session on average chip thickness. It's a pity we have to go for 2 sessions, because milling cutter positioning, the value of it can be only truly valued or appreciated when we talk about average chip thicknesses. And if we talk about average chip thickness, if you can participate, you'll see next time that very often I refer back to milling cutter positioning. So the 2 are kinds of 2 sides of one coin. But anyway, for today, I hope you had an interesting hour. If I look back to the questions you asked, I do think we have had some interesting thinking going on while I was talking, and as I said, I'm looking forward to continue the discussion in the comments or however, because some of the questions you asked, some of the statements you said are very, very valuable and deserve more attention and more discussion, more insight. Thank you very much, and looking forward to see you at the session where we discuss average chip thicknesses and the things that comes together with that. Thank you.